Multi-agent system is a large-scale system which composed of numerous agents with simple intelligence connected through the network. Because of its autonomous and distributed characteristics, connected intelligent agents can collaborate to complete high-complexity tasks. However, in a distributed multi-agent system, it is difficult to coordinate each agent due to the limited communication resources and computing capability. While a centralized multi-agent system faces severe issues due to a huge amount of computing and communications overhead. Stigmergy is an indirect communication mechanism existing in social insect species, which relies on pheromones deposited in the environment to coordinate individual insects' activities, and exhibit strong robustness with a simple form. Inspired by federal learning, we propose a decentralized control model based on Stigmergy mechanism in network-assisted multi-agent system. And we design an experimental scene to mobilize several distributed agents to arrive at tracking points with as few rounds as possible. And exploit Keeper of 4 robots to implement the algorithm in practical settings. This figure shows the decentralized control model based on the Stigmergy mechanism. It consists of 2 parts, that is, DP processor and agents, which form a WLAN to connect multiple distributed agents to establish communication. DP processor collects local information with the precision of temporal synchronization mechanism. With simulating the characteristics of superposition, decay, and diffusion, DP processor generates a DP map and delivers it to agents each round. To prevent information mismatch when all agents communicate with DP processor, TSM is introduced to follow strict timing requirements when interacting between agents and DP processor. Similar to a buffer, TSM sacrifices part of the agent's moving time to coordinate the behavior of distributed agents, as well as reduces the probability of collision between the agents to some extent. Each agent has a definite perception range for pheromone, and the volume of pheromones decreases with the increase of distance, which attracts agents to gather at location with high pheromones volume. However, distributed agents often cannot cooperate well to accomplish tasks efficiently. Under the guidance of pheromones, we use asynchronous advantage actor-critic algorithm and deep reinforcement learning to train the agents. This learning method can train agents' sense of collaboration to take global optimal action in the current state. Agents sense the state of surrounding environment based on DP map, compute the next decision and perform actions. While agents are acting, they simultaneously upload local information to the DP processor and wait for the feedback information of DP processor in a blocking manner. The information uploaded by agents is processed by TSM, and the entire information is delivered to the DP processor. With simulating the superposition, decay, and diffusion properties of pheromone, DP processor merges the collected information and updates DP map. DP processor delivers the updated DP map to each agent, and repeats recursively until all agents reach the target points. We use a PC with a Wi-Fi module as the DP processor and 3 Keeper of 4 robots as moving agents. In the experimental scenario designed in this paper, the objective is that agents who are randomly placed within a certain area reach the target points in as few rounds as possible to form targeted specific shapes. First, we initialize the robots by placing them randomly within a certain area and informing the initial position. In the earlier phase, the general direction of the increase in digital pheromones is perceived, which attract more robots to approach the target points. As the number of rounds increase, distributed robots move into a narrow space closed to the target points, where each trained robot compute the optimal action under the current environmental conditions. Finally, all robots have reached the target point. This figure presents the numerical results in detail. It can be observed that compared to the cases of adopting DP or DRL only, the proposed combination of DP and DRL yields superior performance. It also can be seen that the performance is greatly reduced when the range of agents' perceptual pheromone becomes smaller, from 4 to 3. In particular, DP can attract agents to places with high pheromones volume at the beginning, and DRL can coordinate the behavior of agents when agents move around the target points.